You know these giant AI models like ChatGPT? Ever wonder what's really going on inside their brain? Well, today, we're going to do more than just talk about it. We're actually going to build a simple one, right here, from scratch. We are going to pull back the curtain on the single most important architecture in modern AI, the transformer.
So let's kick things off with a problem, a really fundamental one that stumped older AI models for years. Take a sentence like, "The robot picked up the ball because it was heavy." Now, you and I know it probably refers to the ball. But how does an AI figure that out? This whole challenge of understanding context is the key to everything. See, the old way of doing things with models called RNNs was to read a sentence just like we do, one word at a time, in order. The problem is, if you have a really long sentence, by the time the model gets to the end, it can kind of forget what was said at the beginning. But the transformer, it's a whole different beast. It looks at the entire sentence all at once, in parallel. This lets it see the relationship between every single word and every other word, no matter how far apart they are. And this radical new way of thinking, it came from a single groundbreaking paper published in 2017. The title was almost deceptively simple. Attention is all you need. This paper didn't just improve on the old methods. Nope. It basically threw out the old playbook and started over with a brand new one. The big core idea of the paper was something they called self-attention. And here's the crucial part. For any given word in a sentence, the model can now weigh the importance of all the other words to better understand that one word's meaning. It's like giving every word in the sentence contextual superpowers. So how does this self-attention thing actually work? Well, here's a great way to think about it. Imagine every word is a little researcher. First, it comes up with a question about itself, its query. Something like, "Hey, what other words here help define me?" Then it looks at the headlines of all the other words. Those are the keys to see which ones seem relevant. And finally, once it finds a match, it pulls the actual information, the real substance, the values, from those relevant words to build a new, much richer understanding of itself. And believe it or not, that entire complex process we just described, it's all run by this one single, elegant formula. Now, don't worry about the math symbols. Just think of this as the engine. This is the mathematical heart that makes the whole query, key, and value system tick. So, in plain English, what is that engine actually doing? It's pretty straightforward. It takes our word, the query. Then it calculates a score for how relevant every other word, the keys, are to our word. Next, it uses a neat little function called softmax to turn those raw scores into clean percentages. We call these attention weights. And finally, it uses those percentages to mix together a new meaning from the values, creating a brand new, context-aware version of our original word.
All right, so that's self-attention. It's an amazing ingredient. But how do we use it to build an actual AI? Well, we assemble it into a repeatable unit, something called a transformer block. Let's take a look at the recipe.
You can think of each block like a little thinking machine. First, the self-attention layer does its magic and figures out all the context. Then, a step called add and normalize comes in to keep the math stable and prevent things from getting out of control during training. After that, a standard feed-forward network does some more processing, and then, you guessed it, another stabilization step. The best part? You just stack these blocks on top of each other to create a really deep and powerful AI brain.
But hang on a second. If we're looking at all the words at once, how does the model know the difference between dog bites man and man bites dog? The word order is completely lost. Well, this is where another really clever trick comes into play: positional encoding. It's basically a way to add a unique mathematical timestamp to each word, using sine and cosine waves, so the model always knows where each word originally was in the sentence.
Okay, the architecture is assembled. We've got our self-attention, we've got our transformer blocks, we've got our positional encodings. Now is time for the really fun part. Let's put our new AI brain to the test and see if this thing can actually learn.
We're going to start with a pretty simple task, sentiment analysis. We'll give it a bunch of simple phrases and tell it whether they're positive or negative. The goal is to see if it can learn the pattern. Can it figure out that great movie is a good thing and bad movie is a bad thing?
So we built the model from the ground up, just following the ideas from that 2017 paper. We fed it our training data and we let it run. So the big question is, did it work? Did it actually learn anything useful? The answer is yes, it absolutely did, and it worked incredibly well. After just a short training run, our little from-scratch transformer model achieved 94.2% accuracy on this task. For a model we just built ourselves, that is a fantastic result. And to put that number into perspective, check this out. A model built with that older sequential technology we mentioned earlier, the LSTM, it only managed about 88% accuracy on a similar task. So we're seeing a really significant jump in performance here, and it's all thanks to that core idea of self-attention. But, an accuracy score is just a number. The really fascinating part is to look inside the model's mind, to peek under the hood and see how it's actually making these decisions. What did it really learn about language? To figure that out, let's feed it a new positive phrase, one it might not have seen in this exact combination: great movie love. Now we're going to watch and see what the model pays attention to when it processes each of these words. And here it is. This is the aha moment. When the model is processing the word great, we can see its self-attention mechanism lights up and pays the most attention to the words movie and love. It learned all on its own that the meaning of great in this specific context is deeply tied to those other two words. It's seeing the relationships. It's working. So, to sum it all up, the Transformer's superpowers are pretty clear. It is ridiculously fast because it processes all the words in parallel. Its self-attention mechanism lets it capture those really complex, long-distance relationships between words. And fundamentally, it's just a simpler and more powerful architecture than anything that came before it. And this brings us to one final, huge thought. We just built a simple model from scratch that was over 94% accurate. So what happens when you take this exact same idea, these same building blocks, and you scale it up, way up, with billions of data points and a massive network? Well, you get the giant language models like GPT and BERT that are literally reshaping our world. And now you know exactly how the engine inside them